Alright, hi everybody. Um, I am now about to cover, I'm still going to be talking about limits. This is section 2.2 in the textbook. It is entitled Infinite Limits and Limits at Infinity. Um, these are essentially the limits where one or the other or both of these things can happen, which are you can investigate the behavior of a function as x approaches positive or negative infinity, or you can it might be the case that you have a limit where as x approaches a particular value, the function increases without bound. And to describe that behavior, we would say that the limit itself would be infinity. So one of the main, I guess, purposes of this is to look at end behavior of functions, which some of you might be familiar with from a pre-calculus course. You may or may not. And that may or may not tell you about the existence of a function having horizontal asymptotes or not. Okay. There are also times where you might have a limit where a function is approaching infinity or increasing at a particular x value. That oftentimes is going to tell you about vertical asymptotes. Okay, so there is a relationship between infinite limits and limits at infinity, and what it tells you about the possible existence of vertical and horizontal asymptotes. Okay, so what I want to do is I want to look at a graphical example of this first. So what I want you to consider is a graph of a function here. Here I have included the asymptotes in dashed horizontal and vertical lines. So there is for this particular function, what I want you to notice is that there's a horizontal asymptote of y equals 2, and there are vertical asymptotes of x equals negative 3 and x equals 2. Okay, now again, what an asymptote is, a vertical asymptote is a vertical line that the function the function, I guess, gets close to that vertical line as x approaches that particular value. So one of the vertical asymptotes is x equals negative 3, and you'll notice that either to the left or right of that vertical asymptote, the function is either decreasing or increasing without bound, meaning as you get close to the vertical asymptote, the value of the function will either infinitesimally increase or decrease. Okay, so the function keeps increasing on the right side of negative 3 as the input gets closer, or if you look on the left side of the vertical asymptote, negative 3, the function is becoming more and more negative without ever crossing that vertical line. Okay, the same thing happens at x equals 2. The function either becomes more and more negative or more positive as x approaches 2 from the left or right. And then what I want you to notice is the horizontal asymptote of y equals 2. As you move to the right or to the left, okay, you get farther and farther away from the origin. So if x increases to infinity and you go to the right, you'll notice that the function starts to approach the horizontal line y equals 2, and the same thing happens on the left. Okay, if you focus on this portion of the graph on the left, okay, as x becomes more and more negative, the graph is approaching the horizontal line y equals 2. Now, all of this information can be expressed using limit notation. So for instance, a couple things I could talk about. So I could talk about the end behavior of the function. One thing I want you to notice that is as x approaches positive or negative infinity. Okay, so that's what that notation means. It means as x approaches positive or negative infinity, meaning x is becoming more and more positive or more negative. What you'll notice is that the function values themselves are always getting closer and closer to positive 2. right? So that's what it means to say y equals 2 is a horizontal asymptote. Okay, well that information can also be expressed as a limit. This is the same as saying the limit of f of x, or what is f of x approaching, as x gets more and more positive or negative, and in this case you can write approaches plus or minus infinity. This is technically two separate limits written at once, but whether x approaches positive infinity or minus infinity, the function values or y coordinates are getting close to 2. Okay, so this is what I'm calling these are what I would be calling the limits at infinity. Okay, so x is approaching either positive or negative infinity. Limits at infinity are really just the same as what is called the end behavior of f of x. Okay, so in the top right of the, I guess, whiteboard or screen, that's how you would have maybe described the end behavior in a pre-calculus class, or said that that's the information that tells you y equals 2 is a horizontal asymptote. Or, now that we understand the notation of limits, you can also express that information with the limit notation. Okay, so these, if you look at both of these pieces of information, are equivalent. Okay, they're both saying that the function values approach 2, or the graph of the function is approaching its horizontal asymptote as x goes to infinity or minus infinity. Okay. Now, one thing you can do is if you go back to a minute in the video, I had just said the limit as x approaches plus or minus infinity of f of x equals 2. Since the limit equals an actual value, both those limits are said to exist. Now, what I want you to notice is, I want you to focus on the behavior of the function around its vertical asymptote x equals 2. Okay. Now, I want you to notice that the limit there, as x approaches 2 of f of x, this simply does not exist. Okay, on the right side, the function values get positive. As you approach 2 on the left, you're actually, the function values are getting more and more negative. So that limit does not exist, but what I do want you to notice is that you could write this. If you approach 2 from the right on the x-axis, okay, you're going to notice that, alright, if you approach 2 from the right, what's the function doing? It's growing and growing. It's becoming more and more positive, infinitesimally, or infinitely. So you could describe the right-hand behavior. You could say the function is getting more and more positive or approaching infinity as x approaches 2 from the left. Okay, you could also look at the left-hand limit. And again, this limit does not exist either. The function does not approach a particular value. It just keeps getting more negative on the left-hand side. You could describe that behavior by writing the limit is negative infinity. Okay, both limits do not exist, but writing infinity or minus infinity is just describing the behavior. Whenever you have a vertical asymptote, the right hand or left hand limit at that vertical asymptote is always either infinity or minus infinity. Okay. Or at least one of them has to be infinity or minus infinity. Okay, in this case, both of those limits were infinite. And then these are what are called, if a limit ever happens to equal infinity, these are what I'm calling, okay, these are examples of infinite limits. Okay. And that's a graphical example of what a limit at infinity is. That's just the end behavior of a function, what's happening on the ends. An infinite limit is just any limit where x approaches either a value or infinity, and the limit itself, the function behavior is described by writing either infinity or minus infinity, depending on if the function is increasing or decreasing without bound. Here's another example of a graph of a function. This time I have a single vertical asymptote. This one actually occurs at x equals 2, and I have a horizontal asymptote of x equals 3. Okay, but notice you only approach the horizontal asymptote on the left side. This is a piecewise function. The right half of the graph actually does not approach the horizontal asymptote. It crosses the asymptote and increases without bound. So notice there is still a horizontal asymptote and a vertical asymptote. You could look at the infinite limit on the left-hand side of this function. As you move more and more to the left, the function values are approaching 3. So, right, that's telling you that y equals 3 is a horizontal asymptote. Okay. So if you ever get if a limit exists at infinity or minus infinity, that's telling you about a horizontal asymptote. Notice, though, that the end behavior on the right-hand side of this function, the function just increases without bound if you look at this piece, since it goes up forever as you move to the right. That you could say that the limit at infinity is itself infinity. Now you'll notice that x equals 2 is a vertical asymptote, and if you look at both those limits, and by both limits I mean the right-hand limit at 2, and then you can also look at the left-hand limit at 2. And you'll notice that on the left side of 2, the function decreases without bound. Okay, it goes down forever, so that limit would be minus infinity. But notice that the right-hand limit would be 0. Okay, because the graph is getting closer and closer to the x-axis as x approaches 2 from the right. I should have left myself some room here. I'm just going to rewrite this. Again, the limit as x approaches 2 from the left of f of x was equal to minus infinity. That is what tells you, that x equals 2 is a vertical asymptote. So if at an x value on the left or right hand side, if the limit is infinite, that tells you the x value is a vertical asymptote. Now we're going to do all this algebraically in just a second. So this is how to deal with infinite limits and limits at infinity if you're looking at a graph. And basically all limits are doing is describing the behavior of a function, right? A limit is not talking about what the value of a function is at a point. A limit at a value, either like as x approaches 2 or x approaches infinity, a limit is just telling you how a function is behaving. Okay, so limits are about behavior of functions, not the actual function value itself, so to speak. Okay, so like I was just showing you graphically, there is a connection between infinite limits and vertical asymptotes. So first, read the first box. It's a definition. It says, the connection between infinite limits and vertical asymptotes. The vertical line x equals a is a vertical asymptote for the graph of f, or y equals f of x, if f approaches infinity or minus infinity as x approaches a from the left or from the right. Okay, so what this is saying is, let me maybe summarize this for everybody. Means that x equals a is a vertical asymptote. You can just use the acronym VA if the limit as x approaches a from the right of f of x, this is plus or minus infinity, or you need one or two or both of these things to happen. Or if you look at the left-hand limit at a, that could possibly be plus or minus infinity as well. So basically it just says as you approach the vertical asymptote on the x-axis, the graph should really just be going either up or down on at least one of the sides. Okay. Now, this is not how you locate vertical asymptotes. We can just use algebra or pre-calculus knowledge to find where vertical asymptotes are, but we would verify that something is a vertical asymptote by calculating one or both of these limits and showing that you get infinity or minus infinity. So if you look at the box down here, theorem 1, if you really want to know where your vertical asymptotes are, for a rational function, f of x equals n of x over d of x, you'll see some examples in a moment. Rational functions are just functions where the numerator and denominator are polynomials. If the denominator is 0 at a point, but the numerator is non-zero at that value c, then x equals c is a vertical asymptote of the graph of f. So basically it's just saying that if you plug c into the denominator and get 0, but plug it into the numerator and you get something non-zero, that's a vertical asymptote to the graph of f. So let's do some examples. What we're going to do is we're going to use theorem 1 or algebra to find the vertical asymptotes, and then I'm going to verify using limits. I'm going to use the definition of what an infinite limit and a vertical asymptote, or the connection between them. I'm going to use this definition up here, okay, rephrased in limit notation, to actually verify that that vertical asymptote is indeed a vertical asymptote. Okay. Alright, so example 1, there's two rational functions here. Again, notice it's polynomials over polynomials. And we're going to find the vertical asymptotes of the following functions, and we're going to verify by finding the appropriate limit. Okay, so example 1, what I'm going to do is, it's oftentimes helpful to fully factor the numerator and denominator as you're doing this. Notice the denominator is a linear function x minus 2. There's not much you can do with that. But the numerator will factor as x minus 2 times x minus 3. Okay, I believe that is correct. Okay, and what you're going to notice here is that these two factors are going to cancel. You're just going to get x minus 3 as long as x is not equal to 2. Okay. So what this means graphically is this is a linear function with y-intercept at negative 3. So it's linear function, y-intercept negative 3. The slope is 1, but the function does not exist at 2. So there's probably just going to be a hole there. And what you would notice is the hole is going to occur at negative 1. So if you plug 2 into x minus 3, you get negative 1. So the graph of the rational function just looks like a line with a hole in it at x equals 2. Okay, so this function actually has no vertical asymptotes. Okay, there's only there's a hole at x equals 2, but there's no vertical asymptote. Okay, so that probably was more of a non-example. That function actually does not have a vertical asymptote. Okay, I'll do a couple more examples. So I'll probably do part B, and then I'll make something up for part C. Okay, so Part B, g of x is x squared plus 9 over 4 times x minus 3 squared. Now, I want you to notice that okay, if a d represents the denominator, you're going to notice that d of 3 is equal to 0, but if n is the function in the numerator, n of 3 would be 3 squared plus 9, you get 18, which is not equal to 0. So that theorem tells me that x equals 3 is a vertical asymptote. Okay, so what we're going to do is I want to verify that x equals 3 is a vertical asymptote. I'm going to do this in several ways. The first way is just going to be checking graphically. So I have just come into Desmos and I have graphed g of x, which is x squared plus 9 over 4 times x minus 3 squared. And what you'll notice is that I have also graphed the vertical asymptote in blue. I can make that go away if I want to, but there we go. Okay, and you'll notice that that is a vertical asymptote. Actually, I can just zoom out. You'll notice that on the to the right and left of 3, the graph of g of x is increasing. Okay, and it's just gonna, the closer and closer x gets to 3, the more and more the function values of g of x increase. So that's one way I know that it's a vertical asymptote graphically. And to show that it's a vertical asymptote, algebraically I would have to calculate a left or right hand limit. Okay, so I just verified graphically. So remember, x equals 3 is a vertical asymptote, just knowing what I know from a pre-calculus class. 3 makes the denominator 0, but not the top. Okay, and what I want you to notice is, okay, well, this is how I'm going to verify this algebraically. So on the test, if I say verify algebraically, I'd have to see your work and you'd actually have to show me this limit. So I can look at, you only need one of these, but I can look at the left-hand limit. Oops, let me not write g of x, let me write the x squared. This is g of x squared plus 9 over 4 times x minus 3 squared. Okay, so a little fact for you. When calculating especially one-sided limits where you know that the limit's going to equal, we already know this is going to equal infinity by looking at the graph, but how do I know that? So what I want you to notice is, if you look at the limit as x approaches 3 from the left of the numerator, that's equal to 18, but the limit as x approaches 3 from the left of the denominator is equal to, okay, that is equal to 0. You can just plug 3 in for x. But 4 times x minus 3 squared is always positive. So it's something, the denominator is always positive, but approaching 0. And notice that the numerator approaches a positive value. Now, it might actually be more informative for me to say this. Okay, so note the numerator, whenever the numerator approaches a non-zero value, okay, and the limit of the denominator is 0, but I guess what I actually want you to notice is that x squared plus 9 over 4 times x minus 3 squared, that's always positive if x is less than 3. Okay, so as you approach 3 from the left, that fraction is always positive, but the numerator is going to 18 and the bottom is getting close to 0. So think about a fraction where the numerator grows, but the denominator gets really, really small. The fraction itself is going to be growing. This is an infinite limit. And the same argument, now that would be enough to tell me 3 is a vertical asymptote. Now if I look at the right-hand limit, I only really have to change a couple things. you're actually going to notice that this function right here is positive valued all the time. The only thing I would need to change then over here, it's still true. I can change these. Okay, it's still true that as you approach 3 from the right, the numerator still approaches 18 and the bottom still approaches 0. Plus, there we go. But the function we're taking the limit of, this is greater than 0 if x is greater than 3. That's what tells me that the right-hand limit is also positive infinity. So the fraction is always positive is what I'm saying. If the top approaches a non-zero number and the bottom approaches 0, as long as that fraction has the same sign as you approach 3 from the left or right, so like notice here that whether you approach 3 from the left or right, that fraction or that function is positive. Since the top approaches something non-zero and the bottom approaches 0, okay, that means the fraction is getting larger and larger, but it's always positive. So the left and right hand limit would be infinity. Now, that's just a verify. So again, all I did here was, okay, this is the answer. This was a check. Okay, x equals 3 is a vertical asymptote because one of those two left or right hand limits was infinity or minus infinity. Now let me give you another one where maybe I'll just make up another function. Let me call this part C. Okay. Now what if my function is f of x equals, let's do x squared minus 5 over, let me just do x minus 2 in the denominator. Okay, so what do we know already? 2 makes the bottom 0 but not the top 0, so x equals 2 is a vertical asymptote. And then what you could do now is you could look at you only have to show one of the one-sided limits at 2. So this is the part that on the test I would say, okay, if I say to verify this, then I need to find the limit as x approaches 2 from the left or right. You only need one of them. And sorry, again, I don't want to write f of x. I can just use the function x squared minus 5 over x minus 2. Now again, what I want you to notice is that, let me come off to the side. Okay, the limit as x approaches 2 from the left of the numerator is equal to, well, 2 squared minus 5 would be negative 1. And the limit as x approaches 2 from the left of the denominator is 0. Okay. So notice now that the numerator approaches negative 1, which is non-zero, and the bottom approaches 0. And now, as long as x squared minus 5 over x minus 2, as long as this is either strictly positive or negative as I approach 2 from the left, then that's going to tell me the sign of what sign of infinity I need to use. So I know this limit's going to be plus or minus infinity, but now how does x squared minus 5 over x minus 2 compare with 0 if we're approaching 2 from the left, x is less than 2? Okay, so just plug something less than 2 into that expression. Okay, if you plug, say, 1 into it, the numerator 1 squared minus 5 is negative, and 1 minus 2 in the denominator is negative. Okay, you can check for yourself, but as long as you plug anything less than 2 into that fraction, it will be positive, so I know that this limit is positive infinity. Okay. Now, if you need to go back, you can go back and pause the video there. Now, say I want to calculate the limit as x approaches 2 from the right of this function. Okay, now, again, the bottom, you can look at the denominator. Okay, x minus 2 is, the limit of the bottom is 0. The limit of the top is not 0. Okay, and since this is a one-sided limit, okay, the limit, it's going to be plus or minus infinity. But, okay, how do I choose that sign now? Well, I want you to notice that x squared minus 5 over x minus 2 is actually negative if x is greater than 2. So, right, if I approach 2 from the right, okay, how do I know that this expression is negative if x is greater than 2? You can plug something like 3 in. 3 squared minus 5 is positive, and actually 3 minus 2 in the denominator is also positive. This might be a mistake on my part. And actually my problem here is, let me actually erase this for a second. Let me get this out of the way as well, so I'm not looking at two different things. I guess if you wanted to know the sign, you should probably pick something closer to 2 that's bigger. Okay, so what is the sign of x squared minus 5 over x minus 2? Is it bigger than 0 or less than 0 if x is greater than 2, but really close? It would probably actually be better to plug something like 2.1. Plug something really close to 2 that's bigger than 2 in. You're going to notice that 2.1 squared minus 5 is negative, but 2.1 minus 2 in the bottom is positive. And this expression is less than 0 if x is greater than 2, but close to 2, which is why the value of this limit would be negative infinity. And go graph this function and verify that. Okay, so we just talked about how infinite limits are possibly connected to vertical asymptotes. You saw that graphically earlier as well. Now, I'm going to talk about how limits at infinity really are just describing the end behavior of a graph. By the time I'm done with this handout, you should be pretty good at doing limits at infinity, especially for polynomials, and rational functions. Now, Theorem 2, there are 4 limits here. So first of all, this theorem is going to allow me everything I need to do limits of polynomials and rationals at infinity. So basically the end behavior of polynomials and rational functions. Okay, so if p, just for this problem, if p is a positive real number and k is any non-zero real number, then I've got 4 limits here. I've got limits at infinity and minus infinity for k over x to the p, so dividing by a positive power of x. And then I've also got limits at infinity of k times x to the p. Okay, so for the first two, if I look at the limit as x goes to infinity or minus infinity of k over x to the p, okay, for these two, it's going to turn out that both of these limits are just going to be 0. So again, the numerator is k, which is a non-zero number, and the bottom is Okay, if x is going to infinity, okay, the denominator is getting bigger and bigger. So anytime the denominator gets bigger and the numerator stays the same, that fraction is going to be approaching 0. And in terms of graphically, there's two possibilities for the graph of k over x to the p. So if x is even, or if p is an even power, okay. Like for instance, this is just an example. This would be 1 over x squared. Okay. You'll notice that whether you x approaches infinity or minus infinity, y equals 0 is a horizontal asymptote. Okay, and k, all the k in the numerator is doing a possibly a reflection or a vertical scaling, and that's not going to really change the shape. You would notice, for instance, like here's the graph of, I could look at something like negative 2 over x cubed, for instance, and what that's going to look like is something like this. You're going to be positive valued to the left of the y-axis, and the graph is going to be below the x-axis, to the right of the y-axis. But notice in either of these cases, it doesn't really matter if k, the numerator, is positive or negative, and it doesn't really matter if the power is even or odd of x in the denominator. The end behavior of any functions of these form k over x to the p will be 0. So those first two limits are 0. Okay, for these two limits on the bottom, okay, the limit as x goes to infinity or minus infinity of kx to the p, this time it's really going to matter what the power is, and it's going to also matter what the constant k out front is. Okay, so for instance, okay, let me actually rephrase or rewrite properties 3 and 4. So these first two limits of k over x to the p are 0 no matter what k and p are, whether p is even or odd, as long as it's a positive power and k is any real number other than 0. But the third and fourth limits, those are going to both be plus or minus infinity, and it really depends on the values of k and p. Okay. So, for instance, if you look up here in the case where, if I'm looking at the function kx to the p, where k is positive and p is even, you might want to think of like, okay, how about just the function, 2x squared, for example. Okay, it's a parabola opening upward, so both those limits in 3 or 4 would be positive infinity. Okay, right? As you go to the right, the graph goes up, or as you go to the left, the graph goes up. Okay, I'll give you maybe just an example here as well. If k was positive and p was odd, for instance, like 3x cubed, okay, it goes down on the left and it goes up on the right. Okay, we'll see an example in just a moment. Okay. And then I've got the other two cases. If k was less than 0 and p was even, the graph goes down on both ends of kx to the p. And if k is less than 0 and p is an odd power, okay, the graph goes up on the left and down on the right. So those limits are going to depend on the value of k and what power you're using. Okay. All right. Okay, so I want to basically, again, use that previous theorem, those 4 limits, to find limits of polynomial functions and rational functions at infinity. Now, what this is saying right here is, this is the general form of a polynomial function. For instance, if you look down at example 2, here's an example of a polynomial. It's just all the terms involve powers of x with coefficients. Like the first term is an x cubed with a coefficient of 4. The second term is negative 2x squared, okay, and so on. Okay. Now, two things happen, or what does actually happen here, is these are the limits that describe the end behavior of the polynomial. Polynomial functions either rise or fall on the ends. So whether you're looking at how does the polynomial p of x behave as x goes to infinity or negative infinity, if you look closely there, what it says is the limit of the polynomial function is the limit of the leading term, a n x to the n. Okay, so for example, let me just show you this down here. Essentially what that previous theorem says is that the limit of a polynomial function at infinity only depends on the leading term. And for this polynomial, the leading term is 4x cubed. So if I want to find the end behavior of the function, I can do the limit as x goes to infinity of, okay, the polynomial. Okay. And I'm going to show you graphically in just a second that the end behavior is only going to depend on the leading term, which is 4x cubed. Okay, now, what does this limit equal? Okay, well, think about the graph of 4x cubed. It's an odd power of x with a positive coefficient. The graph looks like this. So the limit as x goes to infinity of the original polynomial is going to be infinity, and the limit as x goes to minus infinity of p of x, that polynomial up there, is the same as the limit of the leading term 4x cubed, and if you look at the graph of 4x cubed, the graph goes down on the left. Okay, so that's the limit of a polynomial function at infinity. It just depends on the leading term. Now, why does it work that way? Why is the limit of a polynomial the limit of the leading term? Well, as x gets really, really large, okay, the term that has the highest power of x is going to make the largest contribution to the entire expression. That would be one way to think about it. The other thing you can do is you can think about this graphically, and let me see if copy and paste works in Desmos. I'm not so sure it does. Oh, it does. Wonderful. Okay, so there's the graph of the function, the polynomial that I'm given, and if I just look at the graph of 4x cubed, okay, what I want you to notice is the farther out I zoom, the functions become indistinguishable. Okay, the only real difference in the function is probably close to the origin. The farther away from the origin you move, like if I keep going to the left, you're going to notice that the graph of the original function and the graph of the leading term just become closer and closer to each other. Okay, so you have the same end behavior to the left. And the same would be true on the right-hand side. Oops. Okay, I'm going to zoom in a little bit. See, you can't even see very much of a difference in the graph of the function and the leading term, okay, until you actually start getting zoomed in pretty close to the origin. Okay, now the last thing I need to do is I just need to talk about end behavior of, or, well, an end behavior of rational functions is related to horizontal asymptotes. Okay. Now, sometimes the end behavior of a rational function will be infinite, okay, and other times the end behavior of a rational function will indicate a horizontal asymptote. So for a rational function on the ends, the graph either goes up or down, or possibly approaches a horizontal asymptote. Okay, make sure you read through Theorem 4 very carefully. Okay, but ultimately what it says, and let me summarize before I go through the examples, or let me actually just box this for all of you. Okay, what I want you to notice is f of x is a rational function, so it's a polynomial in the numerator and denominator. So in the numerator you have an nth degree, a polynomial of degree m, so the highest power of x is m, and in the denominator the highest power of x is n. Well, it turns out that the limit of the rational function as you approach infinity or minus infinity is the limit of the ratio of the leading terms on top and bottom. Okay, and now there's three possible cases for these limits. At this point though, I just do these by hand. I try not to memorize these. So let me go through the examples. So I really only use the fact in the theorem coming from part A. And then if you look at all the cases in part B, you don't really need to memorize those. You should be able to just use some algebra and simplify. So what do I mean? Let me show you. Okay, I've got three rational functions right here, and I'm going to do the end behavior of these functions. So first of all, okay, I'm going to do the limit as x goes to positive infinity of f of x on the left. That's the limit as x goes to infinity of, you're going to take the leading term in the numerator, which is 4x cubed, divide that by 2x cubed, and then simplify after this step. Okay, the x cubes cancel, and 4 divided by 2 is 2. Okay, so let me make some room. You're just taking the limit of a constant, which is a constant. Now it actually turns out you can use the same steps to do the limit as x approaches minus infinity of the function. It's still going to simplify to the limit as x goes to minus infinity of the constant 2, which is 2. And this implies that y equals 2 is a horizontal asymptote, which you can verify by looking at the graph. Okay, and then for part B, this time, okay, I can take the limit as x approaches infinity of f of x, which is the limit as x approaches infinity of the ratio of the leading terms, which is 7x cubed over 3x to the fifth. This would be the limit as x approaches infinity of 7 over 3x squared. So you would cancel 3x squares on top, and you'd be left with, if you get rid of 3 of the x's in the denominator, you'd be left with 2. And we know that if you go to that previous theorem, the limit as x approaches infinity or minus infinity of some number over x to a power, that limit will be 0, and it can also be shown that the limit as x goes to minus infinity of f of x, that's also going to be using the same steps. 7 over the limit of 7 over 3x squared, that will also be 0. That implies that y equals 0 is a horizontal asymptote. Okay, and again, if you graph that function in Desmos, you will see that as you go to the left or right, the function values or the graph approaches 0 or the x-axis respectively. Okay, and then finally, for part C. Okay. Now, what you'll notice in these three examples is, in part A, the highest power on top and bottom were the same. In part B, the power in the numerator was less than in the denominator. In those cases, you're going to get the same left and right hand limit. Now, what do you notice this time? What's different this time, if I'm going to do the limit as x goes to infinity of f of x, this time what you're going to notice is that the ratio of leading terms would be 4x to the fifth over 4x cubed, and then you can simplify, and you will get, I believe, believe, just x squared. So the 4's will cancel, and x to the 5th over x to the 3rd is x squared. X squared is a parabola that opens upward. So the limit of x squared as x goes to infinity is positive infinity. Okay, and it does so happen to turn out that even if you were doing the limit as x goes to minus infinity of f of x, okay, it's still going to be the limit. Since this is an infinite limit and it's a rational function, you can just take the ratio of leading terms, which is still going to be x squared, and the graph of x squared still goes up as you go to the left, so you would still get infinity. Now, it is possible for both these limits to be different. One could be infinity and one could be minus infinity. It just depends on what happens after you simplify the ratio of leading terms for the numerator and denominator. But in parts A and B, in cases like that where the highest power in the numerator and denominator are the same, or the power of the function in the denominator, if the degree of that is higher, you're going to get the same limit as there. Get the same limit there as well. Now, again, here's the shortcut. If you were doing part B, okay, let me just come back to that for a second. You already noticed that the power of x in the denominator is higher than in the numerator. So it turns out it doesn't matter if you approach positive or negative infinity. The limit, the infinite limits of f of x are both just going to be 0. And that's because the power of x in the denominator is higher than in the numerator. Okay, and then same thing for part A. If the power of x in the top and bottom is the same, you're going to get the same limit. And if you look at the ratio of leading terms, 4x cubed over 2x cubed is just positive 2. Okay, so for A, y equals 2 is a horizontal asymptote. For B, y equals 0 is a horizontal asymptote. And then actually, part C, there is no horizontal asymptote because the end behavior was infinite. That's all I got for today. If you have questions, let me know. Hope everybody's doing all right on the homework. I will talk to you soon. Tomorrow is Thursday, and hopefully everybody will be in the Zoom meeting with questions. Have a good day.